Hi, good afternoon. This is Mr. Cassidy, and today I'm covering lesson 12.3, side angle side theorem. So, uh, what is the side angle side theorem? Let's start with a quick overview and begin. So let me get my pen out. There we are. Awesome. So, side angle side theorem is a basic way we can prove that two triangles are congruent. So if I have two triangles, in previous lessons, we were looking at all the sides and all the angles. And once we had named all the sides and all the angles were congruent, we could say that the two triangles were congruent to each other. Well, now we've got sort of a shortcut. It's called side angle side. That means if I have a side touching an angle and that angle is shared by the next side, and that matches with another triangle's corresponding side touching an angle touching another side, excuse my sloppy drawing. So all we need, that is all the criteria we need, because this last side will end up matching up because of the width of the angle. So side, angle, side, those have to be touching this, and that's why we call it side, angle, side. And that's all the information we need to prove the two triangles are congruent. Now this is abbreviated SAS. And so in this lesson, we're going to work on theorems and have some applications using side angle side. So here's the actual explanation of side angle side. You see two triangles and they're rotated, but here we have a side touching an angle touching a side, side touching angle touching side, and therefore we can conclude the two triangles are congruent, which means that really from there, then we could say, yeah, this side matches this side, and we could name the other angles that match up. But for now, that's enough. Basically, we went from the side to the angle to the side and proved the two triangles are congruent. Here's all that gobbledygook about, rotation and reflection that maps it onto each other, but basically it makes two congruent triangles. Moving on. So let's take a look at this. We have two things that are given. We have that side BC is congruent with AD, and we have two parallel lines. And what we want to do is prove that the two triangles are congruent. So I'm going to redraw those. ABC is this one, and I label it. And I just always do this with proofs because I've found it so helpful. I get this here. I'm going to go ahead and mark the parallel part just so I have it. And then I've got the other triangle, CDA. And notice that the word letters, the order matters here. Because what we're saying is that this triangle matches and is congruent. Here's my parallel line. Because this corner, say, of the first triangle, C, has to match with A. And that's because, remember, in our last lesson, the order matters. A is coming first in this one, and it's matching with C in the second. So first, how are we going to prove that? Well, a few things I know. I notice that they share this side. So that's sort of interesting here. And I know I've got parallel lines, and in our 2 chapters ago, chapter 10 or so, we were talking about parallel lines and what those mean about angles, like interior angles. So let's get into our proof. Notice it's already been organized for us, side to angle to side, and this has to be a side clue. And then our final statement, the two triangles are congruent. So let's begin at the beginning. First, how do we know that those two sides are congruent? Well, that was given to us. Next, how do we know those two lines are parallel? That was given to us. Next, how do I know that this angle is congruent with this one? So BCA, I'm talking about this corner here. I'll go ahead and mark it with a single arc. How do I know that BCA is congruent with DAC, which is this one? Remember, 3-letter naming means middle letter is the important one. And here on this one here, BCA, I'm marking here and here. So how do I know those two are congruent? Well, I think if I look back at the original drawing, it's because these two are alternate sides of a transversal. So that would be our alternate interior angle theorem. Angle theorem. That's an angry angle. It's an angle theorem. Next, we're going to need to use the reflexive property. So what is equal to itself that is in both triangles? Well, I noticed, again, that shared side. I already marked it, but CA is going to be congruent here with, and that would be CA, and I want to use side lengths are congruent with AC because of the reflexive property. And last, now that I've done this part, and this part, how do I know the two triangles are congruent? Well, I can say they're congruent because of the side angle side theorem. That's how I know that those two triangles have to be congruent. So I'm going to go ahead and clear my ink. Well, I'll just reveal it all. See all the typing underneath mine. Yep. Side angle side. And I'm fine with people abbreviating SAS. Now that might not work on Big Idea's website, but I abbreviate things SAS. All right, so here's your extra practice. And you could go ahead and try to write the proof, and I'll go over the answers in just a second. Feel free to pause. All right, so I'm going to jump into it. First, I'm going to state my givens. BD perpendicular to AC. AC. And that is given. Next, I know that AD is perpendicular to, AD is congruent with CD. And how do I know that? That was also given to me. Okay, so let's see if we've got any information that helps us towards side angle side. Well, AD is congruent with CD. That's a side. And actually, now I'm a little bit out of order. I could probably put that one first, but that's okay. This would be our angle, because we're going to actually elaborate on that right here. What do I know about these two perpendicular things? Well, I'm going to know that that means that A angle ADB equals 90 degrees. Measure of angle ADB is 90 degrees, and measure of angle CDB is also equal to 90 degrees. And that's the definition of perpendicular lines. And so because of that, I can say that they're both congruent. So angle ADB is congruent, therefore, with angle CDB. And how can I say that? Well, I can say that based on substitution. Or the transitive property might be a little better combo though. And so therefore, I'm going to now, so that's my side. I've got my side, I've got my angle, and now I need one more side to prove it. Well, I notice that they share this side, BD. BD is congruent with BD itself. What do we say when something's congruent to itself or equal to itself? Well, that would be the reflexive. He's flexing there. Property. And I'm keeping this as brief as I can because going on proofs can get a little long. So therefore, I now know, and I have to write up here, my tablet can't write at the bottom of the screen, triangle. I have proved that triangle ABD, and if you're struggling with writing the last line, go back to what they asked you to prove because it's easy to just copy it right from there. That's what we wanted to get to. Triangle CBD. And why? The reason why is because of the side angle side theorem. We had a side touching an angle, touching a side touching an angle, touching a side. All right, moving on. Here I have problem 2. Jn is congruent with Mn. Nk is congruent with NL. Prove J and K, and so I go ahead and sort of trace it so I can see J and K is congruent with M N L. Okay, so from M to N to L. Awesome. So first, let me start with my givens. Jn is congruent. Feel free to fast forward or watch this in twice the speed if you'd like to make my voice a little higher pitched. Given. Next, Nk is congruent with Nl, and that is given. And notice that those are two sides here. So really, all I need to finish proving that those are congruent is that these two angles are congruent. Well, what do I know about those? Angle MNL and angle JNL are vertical angles. And how do I know that? Because that's the definition of a vertical angle. So now that I've proven that they're vertical, I know that those two angles have to be congruent. MNL is congruent with angle JNL because of the vertical angle congruency theorem. And since I've already got all my things listed, now it's a little out of order. I've got the side, the angle, and the side are proven to be congruent for both triangles. I can end with my final statement. Triangle JNK is congruent with triangle MNL. And how do I know? Because of side angle side theorem. Awesome. So how do we use the property of side angle side? Well, here's some real life. Not real life at all, but at some application problems. We know that QS and RP are passing through the center of the circle. So both those lines pass through the center. What can you conclude about MRS and MPQ? I can conclude that those two are congruent. And here's why, is if a line is going to the center of the circle, that makes it a radius. And the radius is going to be equal, and congruent no matter where you draw it in the circle. Second, we have two reflexive angles, so I have side angle side, side angle side, so therefore I can prove that the two triangles are congruent. So here's how this looks in your textbook. You've got, if P is the center of the circle, can you prove that, or what do you know about any two triangles? Can you name two that are congruent? Give you a chance to try it. And you should have come up with the triangle EPF is congruent with triangle GPH. The letter order is somewhat significant here, but I'm doing side angle side. That's how I could tell. Side angle side applies here. Problem 4. ABCDEF is a regular hexagon. What that means is that all these sides are equal. So that gives me a little bit of a hint about what's going on here. And I need to see, are any two triangles congruent? Now, I haven't looked at the answer key in the book, so I'm going to be winging it here with what I see as being congruent triangles. Let's see if I can find them. Well, what I do see is I see that this line FC is bisecting this angle. And it's because it's bisecting, it's cutting in half the pentagon here, hexagon. The same is true here. I've got a bisected angle from line EB here. So if it's bisected, that means that this corner here, corner F, angle AFC, is congruent with corner. Let's see here. Oh, I meant to say this was bisected here. So that makes this equivalent, DEB, angle DEB. There's probably several other triangles you could prove. You could probably prove it with this one and this one. But now I've got those, I've got an angle, and also if this is cutting through the middle of the hexagon, I know that it has to be equivalent to this FC. So I've got FC is congruent to EB because they're both cutting the hexagon in half. They're going from one side to the other, and that has to be congruent because no matter which two I choose that are directly opposite, it'll go right through the middle. Because you'd also think of it as a hexagon inscribed in a circle, and that would be its center. So what have we proved? Well, we've got triangle. Sorry, let me fix that. Triangle EBD is congruent. I should have probably, let me go in a different order. It'll be easier for me. Triangle BED is congruent. So I'm going to go with the side that's half the hexagon first. So that would be CFA. CFA. Now, there's probably many other triangles you could prove, but that's one I did through side, angle, side. I've got the side that's all the way across, the angle that's bisected, and then the side that's on the outside of the hexagon. Okay, carrying on. Here's a quick test problem from our old curriculum. Simone says that the two triangles shown have two pairs of congruent corresponding sides and congruent corresponding angles. Then the triangles are congruent by side, angle, side. So here we've got a side matching a side. Here we've got an angle matching an angle. And we've got one triangle is this one. So we've got angle, side. And the other one is this one. So are the two triangles congruent, angle and side? Do we know if they are? Well, no, we don't. She cannot necessarily say that those two triangles are congruent because we only have two of the corresponding congruent sides. We don't have the second side marked. So we don't know 100%, given what we have here, that the long side here is congruent. So we can't say by side, angle, side that works. We have side, angle, but not the last side. Okay, last proof. We know that PS is perpendicular to, or parallel to QR. And PS, let's go ahead and mark that. PS, parallel to QR. And we know that PS is congruent with QR. PS is congruent with QR. Use side, angle, side to show that PQR, so I want this triangle, is congruent with RSP. Great. So, I know that this side's equal. And I noticed that they're sharing this side, so it'd probably be easiest for me to find this angle is equal to this one. How am I going to do it? I'm going to use two-column proof, and I'm going to start with what's given. PS is congruent with QR because it's given. Second, PS is parallel to QR, and that's given. Next, I'm going to say that these two angles are congruent. And how do I know they're congruent? Well, those are alternate interior angles. So angle PRQ is congruent with angle SPR. And how do I know that? That's alternate interior angle theorem. Interior angle theorem. Next, I can say I've got two sides. I've got the angle. I need the last side that's congruent. In this case, PR is congruent with RP. PR is congruent with RP. Now, I'm not sure if it's necessary to switch the letters. I sort of switch them because the triangle has been rotated. One triangle is 180 degrees, the other one. So what side PR for one, the angles correspond with RP of the other. And how do I know that? That's reflexive. And so therefore, I've got side, angle, side. So I'm going to say, finally, that the two triangles are congruent. So I have proven that they are. PQR is congruent with RSP because of the side angle side theorem. Okay, well, this video was a doozy. Thanks for sticking with me. Thank your minds and your hearts. And I hope you guys are doing well. Stay safe, stay healthy, and I'll see you next week or on Zoom. Feel free to join me, and I'll go over these then. All right. Thanks. Bye.